Welcome back, everyone. It's my pleasure to introduce the second speaker of today's session, Mark Pengitore from the University of Virginia, talking to us about residual finiteness of the mapping class group with respect to solvable covers. All right, go ahead, Mark.
Okay, thank you for the organizers for giving me an opportunity to speak about some of my latest work. Thank you for everyone for coming to this talk or to my presentation. So what I want to talk about is really applying residual finiteness to understand a classic question about the mapping class group. So this is, I think, due to Thurston, and it's been around for a while with many papers published on it, is the mapping class group, MG1. So here, this is the group of isotopy classes of diffeomorphisms of the genus G surface up to that fixed a boundary, a fixed a puncture. Is this group linear? Meaning, does it emit a faithful representation over some field of emit a finite dimensional faithful representation over some infinite field? A faithful finite dimensional finite dimensional representation over some infinite field. Over K infinite field. Now, the thing is that for people who are familiar with basic number theory and stuff like that, there's a lot of different kinds of fields. So even with like even in the most simple case, for instance, C, it's only known for the following group. For the following case, let me get only known for the mapping class group, genus 2 over a puncture, and this is by Bigelow and Bundy in 2001. So other than this result from 21 years ago, not much progress has been made. Now, the thing is that it's kind of it's split in the community whether these groups ought to be linear or not to be linear. So one idea is to find properties of linear groups and when I mean linear, I mean finitely generated linear groups to either give evidence if mapping class group. Okay, thank you. Sammy just said that mapping class groups are not linear and positive characteristics. So I guess then we're interested in characteristic 0. So in particular over C. So, and our focus now will be genus 3 or greater. So give evidence of linearity if our mapping class group satisfies these properties, said properties, or find an obstruction to linearity if it doesn't satisfy one of these. Doesn't satisfy one of these properties. So there's three classic properties, one of which is in the title of this talk. So properties. The first one is finitely many conjugacy classes of finite order elements. And this is well known to be satisfied by both linear groups, at least over linear groups. And here we're assuming over characteristic 0 and the mapping class group. So check, check. Okay, the TITS alternative, which is a very strong structure theorem about finitely generated subgroups. Now these both satisfy it. And then lastly, residual finiteness, which is a strong statement about the subgroup structure or the space of finite index subgroups of our particular group we're looking at. And both the mapping class group and linear groups both satisfy this. Now, it's a pretty simple thing to show that the genus G mapping class group with a puncture is residually finite. This is following from the Berman short exact sequence in an old result of Baum's log. But the problem is that, well, this gives evidence of linearity, all three of these. The issue is that it doesn't actually give much structure in the sense of like what happens, whether it doesn't tell us enough. But what you can do is we can actually, whoops. Yeah, I'll just do this. Okay, what we can do is we can quantify these properties. To see how close they match the behavior of linear groups. Okay, so as a quick reminder, this is due to Maltsev. We have that if G is a group, which will always be finitely generated, we say G is residually finite if every element can be detected using a finite quotient. Residually finite if for all 9 identity elements, there is a surjective morphism from G to a finite group, Q finite, such that phi of G is non-trivial. Okay, so when I say quantify, what do I mean? Well, the idea is that, well, we have an input complexity. And for us, since a lot of us like geometric group theory, this would be word length. But what would be the output complexity? Well, we know that we can always detect an element using a finite quotient. So why don't we just minimize over all finite quotients that detect element? So minimize over all finite quotients which C our element. Okay. So the following definition is due to Burabi in 2010. And as I write this out, I want to mention that this started a whole subfield in group theory where they're trying to understand complexity properties associated with various generalizations of residual finiteness. But our focus will be on residual finiteness. The residual depth function, and from now on, all of our groups are residually finite. Of G, well, this is given by D of G of little g, and here G is non-trivial. This is the minimum over all finite groups such that minimum of the cardinality of the group such that there is a surjective homomorphism from G to Q seeing the element G. So here what we have is that we now have a measure of complexity, or output complexity. So now what we can ask is, what is the complexity of residual finiteness for a linear group? And this was done by Burabi and McReynolds in 2014. You have the following theorem. Burabi, McReynolds. And the idea is that if G is a finally generated group where G is a subgroup, GLN K for some infinite field, then the characteristic here does not matter. It can be a transcendental extension or polynomial, a transcendental extension of a characteristic P or characteristic 0 field. It can be a field of polynomials with coefficients in FP and where you formally invert them all. But what we have is that with respect to any finite generating set, we have that this depth function is bounded above by C times the word length to some D, where D is universal. So now what we have is we have a measure of complexity to compare that of the mapping class group with linear groups. So what do we have here? We have a two-prong, we now have a fork at our road, and the path you take will determine the kind of results you will try to prove and what they will say about possible linearity of the mapping class group. So we have a choice to make. If you show that if you show that the depth function, which I'll just now denote with D, of gamma, where gamma is a non-trivial mapping class, is bounded above, and oh yeah, here this is a constant, which is also universal, times the mapping length of the mapping class element or mapping class, and this was with respect to your favorite finite generating set, where D is some natural number. This doesn't say necessarily that your group is linear, but you have strong evidence. And what I mean by that is, one, the complexity of the space of finite index subgroups or finite quotients of the mapping class group is similar to that of a linear group. in fact, solving the word problem using finite quotients is actually a polynomial in complexity, which is similar to that of a linear group. What's the other choice? Well, if you can show there exists an infinite sequence of mapping classes such that d of gamma I is super polynomial in gamma I, then, and I want to emphasize this, mod G1 is not polynomial. So the first choice, you'll give evidence of linearity. Second choice, you completely obstruct linearity. So if you were to go with the first choice, one way to go about it is to say, well, the mapping class group is the orbital fold fundamental group of the moduli space, and then you start working with that. But what I'm going to go with is number 2. Okay, so we will go down road 1 or road 2. So now the question is, how do we show or how do we compute d gamma for any mapping class? And remember, we're assuming that our genus is 3 or greater. Using work of Franz, you can actually show that the depth function of the genus 2 mapping class group is at most polynomial of 64 squared minus 1 degree. I can explain where that comes from later, but I just wanted to mention that. Okay, so in order for the depth function of any mapping class, and remember this only makes sense when it's trivial, non-trivial. So in order for this to be bigger than any constant, you need for all finite quotients of the mapping class group, so phi from mod G1 to some finite group Q, where this is strictly less than K, then phi of gamma is trivial. So this is saying that when you look at the mapping class gamma, you cannot do better than the value K to determine or to detect it using finite quotients. Here's a major roadblock that we run into. What do finite quotients of mod G1 look like? Well, this is a hard question. It's very mysterious. So if you were to have a bag of all the finite quotients of the mapping class group and stick your hand in there, you don't know what you would grab. So what we're going to do is we're going to introduce what are called principal congruence quotients. And these are mapping classes, quotients in the mapping class group that we can get our hands on. They're very explicit and they come from the geometry of the surface. So suppose you have a characteristic subgroup of the fundamental group of your surface. Well, and we're also assuming it's finite index. Then we have an induced map from the mapping class group to the automorphism group of pi1 of sigma g mod k. Now this typically will not be surjective. And the reason why this map exists is because the mapping class group is an index 2 subgroup of the automorphism group of the fundamental group of the surface. So the image of phi is called a principal congruence quotient. And we denote it as mod G1 bracket K. Now, the reason why I don't put pi1 sigma G mod K into here is because different Ks will give you different morphisms to the automorphism group of the map of the characteristic quotient. And these don't have to be isomorphic as groups. They can even have different sizes. So it's important that you do a marking with respect to the finite index characteristic subgroup of the surface group. So next question is, how prevalent are these quotients?
So, sorry, can I ask a question?
Yeah.
So your mapping class group is for genus G surface with one single boundary.
Yeah.
And your surface is sigma G without boundary.
Yeah. A puncture. So what happens is that using the Berman-Short exact sequence, you have that the mapping class group genus G with one puncture fits into a sequence where you have the point pushing subgroup is the kernel, and then the quotient is the mapping class group of genus G.
Yeah.
Right.
So this sigma G has one puncture. That's what you mean.
No. Sigma G does not have one puncture. The reason being is the mapping class group of genus G with one puncture sits inside of the automorphism group of the genus G surface with no puncture. Of the fundamental group of the genus G surface with no puncture.
Okay, I see. So the first step is adding the puncture map and the capping map, and then you forget the puncture.
Yeah, that's right.
That's what it is. Yeah. Thanks.
So the question now is, how prevalent are these quotients? And this actually comes to the next roadblock. And it is congruent subgroup question, congruence quotient or quotient problem. And the idea is, if phi from mod G1 to Q is a finite quotient, okay, then is there a characteristic finite index subgroup K inside of the fundamental group of our surface such that we have a factorization? So we get mod G1 to Q, then we have a projection down to this quotient here, and then we get a factorization. So the thing is that while there are a lot of these quotients, these congruence, principal congruence quotients, we don't know how prevalent they are. You can always detect an element of the mapping class group using congruence quotients, principal congruence quotients. But this question here is open. Okay. So what we can do though is just go, well, we don't know what a general finite quotient looks like, but we know what these look like. So what we can do is we can do a modified depth function, which I'll call PD of gamma, which is called the minimum over all mod G1 K, where if this is the natural map, phi is the associated quotient map, the projection, then phi of gamma is non-trivial. Okay, so the reason why I'm taking you all down this road is because this is a hard question. There's a lot of problems and open questions and open conjectures that one has to deal with if you want to solve this problem. So then you may ask yourself, what hope is there to do anything? Well, you can have an incremental program here where you go, well, let's first look at these principal congruence quotients. So we now have the roadmap. Okay. One, and this is to showing nonlinearity. Of MG1. Okay. The first question we have is the following. Just split all principal congruence quotients into 3 buckets. And I'll tell you what the 3 buckets are, or 3 piles. Okay, first pile is actually, we find infinite sequence of mapping classes so that mod G1, okay, so that it is exponentially or super polynomially hard and this is in word length, to C gamma I using quotients of the following form, where pi 1 sigma G mod K is solvable. So what we do is we call these quotients principal quotients of congruence type, of principal quotients, principal congruence quotients of solvable type. Okay. The next bucket, as one may guess, is actually coming from the fact, that we have a decomposition of all finite groups into solvable groups, and then next into finite products of finite simple groups. So finite product of finite non-abelian simple groups. So the idea is we want to find an infinite sequence of mapping classes that are hard to detect using congruence quotients associated with finite simple characteristic quotients, or finite product of finite non-abelian simple quotients. And we call these finite congruence quotients of simple type, or semi-simple type, since these aren't necessarily simple. Three, we do all the same. So then now, this is neither. So this may seem like you're just doing two specific cases and then everything else. But the idea is that every finite group is built up from finite simple groups and finite solvable groups. So if you can build up, understand how to work with the finite solvable case, the finite semi-simple case, and then understand how to put them all together, then you'll be able to show that this function here is super polynomial. And then finally, if you can do the first three, you can do, then you can finish the program by showing there's a positive solution to congruent subgroup property, congruence quotient problem. So what I've given you all is a long journey to possibly to show that the mapping class group with one puncture, genus G greater than or equal to 3, is nonlinear. If you could do all 4 of these steps, you win. But every one of these steps is hard. But fortunately, Thomas Colbert and I have solved the first step. So this gives us our theorem. And this is currently being written up. Should be coming out here in a few months. Okay. So there is an infinite sequence of mapping classes. And of course, we're assuming that our genus is greater than or equal to 3, such that there exists an infinite sequence of mapping classes and universal constants A and B, both greater than 0, such that if rho is a principal congruence quotient, a rho is a map onto a principal congruence quotient, and here this is the map induced by the projection onto the finite simple, projection onto the finite solvable characteristic quotient, where mod G1 of K is strictly less than A to the word length of gamma I to the B, then rho of gamma I is trivial. And this is in progress, as I said. So let me interpret this for you all, for everyone. The idea of this theorem is that you cannot see linearity of mod G1 if it were linear, so it cannot see possible linearity, using actions of mod G1 on pi sigma G mod K, where K, this is finite and solvable. So, or interpret, this is not the idea, this is the interpretation. So, however, if you were to show it linear, if it was linear, you would see linearity, or you would see evidence of linearity by actions, excuse me, of the mapping class group on pi 1 sigma G mod K. And this is a finite product of finite simple groups that are non-abelian. Right. So the next step in this program is start looking at how mapping class group acts on characteristic quotients of the surface group, which are finite products of finite non-abelian simple groups. Okay, so in the last 5 minutes, let me give a flavor of the method of proof. I got 5 minutes, right? Or I finished?
Yes,
5 minutes.
yeah, 5
Okay.
minutes.
Okay, great. Step one, what we're going to do is we're going to start with finite characteristic quotients, which are nilpotent. And here, the main tool is to associate a linear algebraic group to the mapping class group mod the ith term of the Johnson filtration. And here, this is the kernel of the induced action of the fundamental group of the mapping class group on the fundamental group of your surface mod the i+1 term of lower central series. This is a linear group, so what you can do is you can take the Zariski closure, which is now a linear algebraic group, which is a short exact sequences kernel nilpotent group, and quotient being the symplectic group, 2G symplectic group, 2G symplectic group over the rationals. And at this point, what you start doing is you start using symplectic representation actions on curves in the surface. In particular, you start by inspecting the action of the mapping class group on given a loop in the surface, there exists a finite cover of the surface such that the lifts of the loop are simple. Can we say something about the structure of the mapping class group after we lift to a suitable cover? For instance, being the product of the most two dank lists. I don't know. Part of the problem is that there's a lot of information about the finite cover that you can't see using lifts of simple loops. For instance, the homology of the subspace of the homology that's spanned by lifts of simple loops is a small subspace in comparison to the entire homology. And this is work of Coberta and Ramajan. I don't know how to say his last name. So on the curve, where these curves are given by, what you do is you take your torus, your genus here, this is the genus 3 surface, you carve out a one whole torus, and then your loops are given by A and B, and we'll look at iterated commutators of that. Step 2, we start hitting it with combinatorics of finite simple groups. In that, finite simple groups are built in a very concise way from finite nilpotent groups. So this gives us an inductive strategy. And then finally, the third step is to use these ideas called laws of finite groups. Okay, thank you.
Thanks, Mark. Maybe we should start with questions from Zoom. Are there questions from the online audience?
Can I ask a question? Sorry. Hi, Sammy. Hello. Actually, yeah. First of all, that was a nice talk. But you said that, can you, well, okay, I don't know if you can go back to that part of the, but you said something about conjugacy classes of finite order elements.
Yeah, there's finally many of them.
In a finite, in what kind of group of finitely generated linear group?
Yeah, so let's say that you're over C, for instance.
But I was under the impression that that was not true. I think I was under the impression, for example, that in SL2R cross SL2R, you can find even finitely generated discrete subgroups that don't have this property.
So let's see, SL2R.
Like,
Are they finally presented?
So I think in SL2R, I don't know if there are finitely, or there are known finitely presented examples in SL2R cross SL2R, but I think in SL2R cross SL2R cross SL2R, you can find even finitely presented examples.
Oh, okay, okay.
Or maybe not SL2, but I saw H2, but then, I mean, maybe you can.
Okay. Yeah, I
but
guess
even,
what I have in my head, I should have written this down. What I have in my head is like subgroups of GL and Z. So it's true there.
Somehow this also
Unless I'm saying something silly, it's very possible.
well, I mean, I think well, okay, I'll I'll think about it, but thanks again. Yeah.
Okay, any other questions from the speaker or the participants that are online? Okay, can you turn the camera on? Is it possible? Oh, maybe not. Okay, so you cannot see us, but are there questions from people in the room? So do you have ideas to attack the next steps, Mark?
Yeah, I do.
Yeah,
I have.
okay.
Yeah, there's actually a pretty precise description of what the principal congruence quotients of semi-simple type look like.
Okay,
And a lot of it has to do with the I never say this right, the Vigo conjecture, which is a conjecture of the action of the free group on generating K tuples of finite simple groups. You can associate a graph to this. And if this graph is connected, this says that your generic characteristic finite semi-simple non-abelian quotient is very, very big. So the associated principal congruence quotients are enormous. So then the problem, here's the problem though, and this is why it's not already done, is that there are characteristic quotients of the surface that are simple non-abelian finite.
mhm,
So this means that there are quotients of the mapping class group that are simple.
yeah,
So you have to simultaneously deal with finite quotients of the mapping class group, which are simple, and then also are like K copies of the simple group where we have an action of the alternating group on the K copies of the simple group.
okay. Okay. All right, any other questions? All right, thanks, let's thank Mark one more time. And our next talk will be in about 10 minutes.